All right. Today we do the daily problem. Hopefully. Whoops. um. All right. Oh yeah, I missed yesterday's. As in, I tried it, but I couldn't get it. I also want to time myself. I feel like I need to get good at Wait, is it a hard problem? No. Okay. I'll give myself say 30 minutes. Be generous to me, just because stuff can get hard. I am recording. Yeah. Okay. Good. All right. Um, let me just change the title of this one. No, what? Give me the. Okay. POTD. This one. Ooh, rhombus. Alright. Get the biggest 3 rhombus sums. Oh my god. Okay. You're given an M by N grid. Hello. That's the grid. Okay. A rhombus sum is the sum of the elements that form the border of a regular rhombus shape in grid. Let me say that again. A rhombus sum is the sum of the elements that form the border of a regular rhombus shape in grid. So like, okay, I can see. So like 1, 2, 3, 4 makes the border. And so this, I guess the elements in there would make the rhombus sum. The rhombus must have the shape of a square. Okay, that is not what a rhombus is, but fine. I can respect that. Rotated 45 degrees with each of the corners centered, with each of the corners centered in a grid cell. Sure, yes, that's what this is, yes. The corner is centered in the grid cell. Below is an image of 4 valid rhombus shapes with the corresponding colored cells that should be included in each rhombus sum. Right, sure. Note that a rhombus can have an area of 0, which is depicted by the purple rhombus. Wow. Return the biggest 3 distinct rhombus sums in grid. If there are less than 3 distinct values, in descending order, if there are less than 3 distinct values, return all of them. Wow. I don't understand what's happening. Where does the concept of color come from? Like, what? The rhombus sum is the sum of elements. You're given an m by n integer grid. It's just integers, right? So can I just pick whatever values? I can pick whatever. I can make whatever. Right. So blue is the 23 200. So I guess, okay, so I'll just screenshot this so I can draw on it. No, what? Oh, because I'm... No, that didn't make sense. Okay, hang on. Wait, what? Why do my screenshots not... Do they go here? Oh my god, they go to the drive now because I said it like that. Okay, fine. What? Bit of technical difficulty. Apologies. What? Okay. Well, okay, fine. That's never happened before, but fine. Okay, so like for example, naively you might think that like this is a good rhombus to try because it's like a big rhombus, but it doesn't have that 200. So even though the sum of it would be 20 plus 8, 20 plus 8 plus 12 makes 28 plus 12 is what, 40? 44, 46, 51 or something. 51 is not one of the big, whoops, 51 is not one of the biggest 3. So then, you'd much prefer going like that. My understanding is you'd have to check every rhombus, but maybe that's not true. Bear in mind that, so you got m over here, 1, 2, 3, 4, m equals 5. That's a 5. And n being number of columns, 1, 2, 3, 4, also 5. Okay, fair enough. Like, you can like check. Maybe this is like DP. I don't know. Like for area equals 0, right? For the rhombuses of area equals 0, that's just individual cells. So maybe you just take the three biggest numbers, like 200, 40, 30 or something. 200, 40, and 30. And then for area equals 1. Wait. Maybe area equals 1 is a dumb way of talking about it. Maybe we'll say side length. Like side length of 0, side length of 1. Because then I know what I'm talking about. Like this is a side length of 0, just the empty rhombus. And then like this is side length of 1. Like 1, 1, 1, 1. And then side length of 2 would be like 1, 2, 1, 2. Oh, that doesn't fit. Like that. 1, 2, 1, 2. And it's like, surely there's a way of figuring how big are the constraints? Because I will inform everything. 10 to the no, that's fine. 50. Okay, yeah. So the grid is relatively small. That's good. So that probably suggests that an n squared solution is expected. So how many rhombi do you expect, right? You've got m by n for there are m. So if I was to do a count, side length equals 0, you expect mn rhombi, right? For side length equals 1, what would you expect? Well, you can't have a rhombus here because that will like go off the page. So you would start here, here, and here. Again, you can't go here because it would go off the page. So you have 1, 2, 3 across, and then you have 4, 5, 6. Then you have 7, 8. Oops, I missed 9. So thinking about like the top corner as like the characteristic corner of like where the rhombus starts, so to speak, there are 1, 2, 3 by 1, 2, 3 positions that are legal. So there's 9 in this case. You know, you can be here if the how do I say, if the rhombus starts in one of these 9 cells, then you'll have a valid side length of 1 rhombus. So in this case, now how would I write that? So how do I figure that out using m and n? So the rhombus, it would be like m minus 2 by n minus 2 rhombi. So how do I figure this out? Basically, like, these guys aren't valid spots to start. Maybe a good way of thinking about it is like talking like the diameter, so to speak. Like the diameter of the, what do you call this? The diagonal length of the rhombus. Because if you increase the side length by 1, you increase the diameter length by 2, right? Like for a rhombus of area 0, side length is 0, and diagonal length is 0 also, right? Diagonal length is 0. If you have boom, 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 side length is 1, and the diagonal length is 2. Side length is 1, diagonal length is 2. If you have like 1, 2, 1, 2, 1, 2, 1, like that, then I think the diagonal length becomes 4, because you got 1, 2, 3, 4. So SL equals 2, D equals 4. So I think you can always say that diagonal length is 2 lots of side length, which I don't know if that's important, but it's just nice to know. Something, just an observation to register. And yeah, so like that's a diagonal length of 1, that's a diagonal length of 2. I'm like defining diagonal, I'm defining a unit very strangely, but it's fine. The reason I'm doing that is basically I'm saying how, like, if you were to start a rhombus up here, how many cells do you need beneath in order to create a valid rhombus? You know, so for a side length of 1, you'd need to make sure you have 2 cells beneath you, right? And same thing, like you would need to have 2 cells across. if you were to have a side length like this. So that should be enough to figure out a formula for the number of rhombi of a particular side length. Like for side length of 1, where are the valid starting places? It's all the places where the diagonal length is, like where you're not going to exceed, wherever you don't spill off the page. So bearing in mind that you need to go to the left by 1 and go to the right by 1, and you have to go down by 2, 1, 2. So for side length 1, you need to basically, I'm trying to think what the easiest way of talking about this is. You need to n minus 2 starts here, and because I can't start here, because I can start here and make a one side length like that, but I can't start here because I'll spill off the page down here. So it's n minus 2, and it's m minus 2 and end minus 2. But how do I decide minus 2? What is the... Maybe it is just a matter of like 2. So n minus 2, which is like n minus maybe the... Is it about the diagonal length? And then m minus the diagonal length? We can test that. So for side length equals 2, there's only one valid position to start. There's only one valid start position, right? Because you can only really be here. 1, 2, 1, 2, 1, 2, 1, 2. So the diagonal length is 1, 2, 3, 4, which does track actually. M minus 4, n minus 4. So maybe the formula for the number of rhombi. Let me try that for like a non-square grid. If I have like... I'm not fully across why the formula works exactly. Like it's a bit of a weird one, but I think it does kind of make sense. So like n equals 3 columns. M is equal to 1, 2, 3, 4, 5, 6 rows, right? So the number of SL equals 0 would be m times n, which is 18. Number of SL equals 1. So we can confirm it's 1, 2, 3, 4, which would be... So, and by our formula we said m minus diagonal length, which would be 2, n minus diagonal length, n minus 2. So it's 4 times 1, which is equal to 4, which tracks 1, 2, 3, 4. Now in terms of a size of 2, I think there should be 0, which makes sense because what if I hang on, let me make it slightly bigger. So ignore, I back these formulas for SL equals 0 and 1. What about SL equals 2? 1, 2, 1, 2. I think I need 5. Because then I can get 1, 2, 1, 2, 1, 2, 1, 2. So in terms of SL equals 2, it would be m minus 4, because diagonal length is 4, n minus 4. So you've got 2 times 1, which is 2, and that tracks because you go here 1, 2, 1, 2, 1, 2, 1, 2, and then you can't go any further down because you'll spill out. You can't go any further to the left or right because you'll spill out. Okay, so yeah, I back this formula. So for side length equals L, diagonal length equals 2 lots of side length, 2L, and number of rhombi that exists in an m by n grid is m minus 2l, n minus 2l. Is this helpful? I've got no idea, but I've used half my time figuring that out, so good stuff. So we have this thing, big squares. Now, I really think that the grid is small enough for us to basically go through every single one of these, because the total number of rhombi, I'm just doing like a constraints check, right, is equal to, m minus 2l, n minus 2l, where l, it's the sum of all these, where l ranges from 0 up to like, I don't know. How big, what's the biggest one you would be able to, what's the biggest thingy you'd be able to fit? Well, you would take we take the smaller of m and n, and then ask, okay, what's the biggest L such that m minus 2L is still positive? If we pretend m is the smaller one, just for without loss, like using a symmetrical argument, without loss of generality, if we pretend m is the smaller one, m minus 2L should be m minus 2L should be bigger than 0, which means 2L should be smaller than m, which means L should be smaller than m over 2. So in general, because it would be the minimum of m and n divided by 2, I think. So L ranges from that to min of m and n over 2. So it's roughly like mn plus m minus 2, n minus 2, plus the dot plus. We pretend, let's just say that it's, let's just say m is the smaller one. M minus, like how many terms are there is what I'm asking. Like m over 2 terms. So it's like m squared n time kind of thing. Which, since it's 50, should be fine. 50 cubed is like not that big, right? 50 to the power of 3? Yeah, it's fine. Okay, so we check every single rhombus. We brute force our way through. It'll be fine. Now I just need to make sure I'm able to like... Oh, actually, is it fine? Because if I don't sort of manage to pre-compute... That's under the assumption that... Well, to be fair, if that's 125,000, then manually like rechecking every rhombus shouldn't be that big a deal, right? Okay. So let's just start by writing what I think will be a valid for loop. For L, for L in range 0, I don't need to write 0, up to this value. Maybe I'll just say while true for now. Start with L equals 0, and then L plus equals 1. Number of rhombi is equal to our formula. M, I need to get M and L. M equals the length of grid, and N equals the length of the first row, or whatever, like the number of columns. Num rhombi is equal to M minus 2 times L times N minus 2 times L, right? If the num rhombi is less than or equal to 0, then just break out, because if, like, at this point, this is probably easier than trying to be really precise with the L values. At this point, we know that L can't be this big because we're not going to get any rhombi, so that's fine. 3 best answers, or 3 biggest sums is equal to none, none, none. 10 minutes. Okay, so it's just brute force. We've confirmed that brute force will work. For do I want to compute where the starting position should be? Like for the size 1, it should be the middle 3 rows in this case. Like you shouldn't. Starting position columns is the range from this is a bit annoying actually. I think go up the side length. So like side length up till n minus 1 minus the side length. Maybe just n minus 1 because the range will be inclusive, non-inclusive. And then starting position rows will be 0 up to you're allowed to, so the range is like here for, I need to get rid of all this random crap. So what I'm basically trying to do is describe the region of space where the rhombi can start, which should be this region, because you can, each of these cells represents the topmost vertex where, for example, length of side 1 rhombus could start. Start again meaning the top vertex. So for L equals 1, for L equals 1, given this particular grid, you have n minus, so yeah, L as the first index, and then n minus 1 being here as the index that you can't go to. So that's what I'm saying. And then here, you can have 0 as the first index, and then 1, 2, 3 doesn't work, because I think if you were to go to 3, you wouldn't have enough space to make the full diagonal. So you can only go up to here. So it would be, if this is m minus 1, you need to give enough space. It'd be m minus 2l, I think. 5 minus, so 1, I think that's right, m minus 2 times l. And then, can you have a length and a range? Is that a thing? Anyway, for row in range, no, for row in starting position rows, I think, for column in starting position cols, we'll have a separate helper. Def calculate rhombus length, sum, I mean, so self, 6 minutes, come on, self, given the particular row start and the particular col start and the side length, L. So sum, the R sum, rhombus sum, is equal to self.get row start, which is R, col start, which is this one, and L, which I'm just storing as L, right? So you do all that. If I don't know. If our sum is greater than 3 biggest sums at -1, then 3 biggest sums at -1 equals our sum, and just sort it. Wait. If 3 Maybe I should just be like negative float inf. It's probably better, eh? Because sums.sort reverse equals true. Okay, so now I just have to do this last bit. Okay. Okay, I can do this. So R is equal to row start. I need the grid as well, don't I? Grid. C is equal to col start, and then just remember to pass that through. Wait, what? Where's the... Oh, I didn't actually do this correctly. Grid. Okay. Sum is current sum is equal to 0 for... Okay, so we're gonna... let me just think about this. So we have some kind of grid, and let's say L is equal to 2 in this case, and we have some position here. This is my current row, and this is my current column. I want to basically take this sum and then go 1, 2. Then I want to go 1, 2. Then I want to go 1, 2, and then I'm going to go 1, and then not 2 because I've already counted this guy. Or maybe I could do, maybe I don't have to count it straight away. So yeah, maybe I won't. For in range L, R minus equals, no, we go down a row, but we go to the left by a column. Current sum plus equals grid at RC. For this one in range L, so this is going down and left. This is going down and right. So that's going to the left. Now we're going down. And then for in range L, R minus equals 1. We're still going to the right though. So that's like, so this is down and left, down and right, up and right. And then we're going up and to the left. So R minus equals 1, C minus equals 1. And we can comfortably just, and then just return. I really hope this works. Actually, the only issue is if L is equal to 0 and it can equal to 0, then none of these for loops will run, right? So I'll just do it like if, I'll just do it as a separate case. If L is equal to 0, return grid at RC, just as like a base case. Otherwise, being 1, 2, 3, and 4, yeah, it should be fine otherwise, I hope. I just have to do some extra pre-processing, because I need to make sure if they're like equal answers, then I shouldn't, answer equals, okay, 4, oh, I'm gonna run out of time. Oh, so close. For, oh, I'm panicking. For num in my answers, 3 bigger sums. If num is not equal to negative float inf. Oh wait, this isn't gonna work. Oh no. Answer equals this one. If it's not this, return, no, not return, ans dot append, no, append num, and then answer equals list set answer, just to get rid of duplicates, and then answer dot reverse, answer dot sort. Okay. if answer's not, if it's not a float, that means we've replaced it. Append it, and then just get a set to make sure it's that. Make it a list because we meant to return a list, and then, right? Yeah, and then just sort it again. God. I mean, I don't. There might be some issues, but shit. Oh, what? I guess my. My ranges weren't so correct. Row start, col start, everything. I think this function, like this method, is fine. I don't think there's gonna be particular issues here. I think it's the information that's being fed is wrong. Although, oh no, it did fail the first test. I was gonna say maybe it passed a couple of cases before it failed, but no. Okay, well, we tried. We almost got it done, but I made a mistake somewhere. So, okay, now that the time is off, we can try and be a bit more accurate because I definitely need to get better with time, like thinking about time. Let me use the lasso. Okay, so let's just think about this clearly now because no time pressure. So let's just get this done. So let me make sure I can like basically prove my formulas. So we have some kind of m by n grid, right? In order for, like, let's think about the criteria. In order for a rhombus of size L, for example, let's say L equals 2, to fit in starting at a particular position, we need to make sure there are L number of spaces to the left, L number of spaces to the right, and 2L spaces down. So you can go 1, 2, 1, 2, 1, 2, and 1, 2. We saw that by like playing around with the example with this screenshot, that like how that kind of works. Right, I'll use black. Like for L to fit twice, we need 2 spaces to the left, 2 spaces to the right, and a total of 4 spaces down in order for this to work out. So long as that criteria fits, so L to the left, L to the right, and R down, 2L down, where did R come from? 2L down, then this spot here is a valid starting point for the rhombus. That was my thinking. So how do I know that that's the case? Well, the starting point needs to be L, like if this is index 0, the starting point needs to be L places to the right of 0, right? So that there are L places to the left of the starting point. It needs to be at least L places to the left of the ending point, so that there are L sort of places to the right of the starting point. So how do I write that? So this is 0 plus L to get that many. So it would be n minus 1 minus L, but that would be the inclusive index. So I add 1 to make it the exclusive index, which is, I think, is what I wrote, right? Yeah, n minus. Ooh, wait. This shouldn't say 1. It should say L. I wrote my formula wrong. And then, okay, let me just, before I move on, let's just check this. So then by a similar boat, we said the starting point needs to be at least 2, there needs to be 2L cells, like 1, 2, 3, 4, right? Beneath the starting point in order to make the rhombus of size L. So the way I can think about that is, well, this is m minus 1, this index. So if I subtract 4, 1, 2, 3, 4, that'll give me the inclusive index. So m minus 2L will give me the exclusive final index, and the starting point can start at 0. That's fine. So that looks right. M minus 2L is the exclusive index, 0 is the starting. Obviously, I don't need to write 0, but it's just nice to have the full thing. And then for R in starting position, for C in starting position calls, you try every single, basically we are describing, in this case, we are describing for m equals 2, well, we'll do L, for L equals 1, let's say. If we were to follow the formulas, we'd be getting from here to here and from here to here. Right, because m 0 plus 1 gets me to here. N minus 1 gets me to here is the exclusive index, so this is the inclusive. So that's like the width of the range, and then the height of the range, we're saying from 0 up to 2 times m minus, from 0 up to m minus 2 times l. So from 0 up to m minus 2l, so 3. 0, 1, 2, 3. So this is the exclusive index, which means this is the inclusive index. So this is my sort of search space for all the valid rhombi of size 1, starting points. Right, so then, okay. I back this a bit more now. Maybe? Ooh, while loop? Did I increase L? I did. Interesting, okay. That's more positive though, because that means that I mean, this should eventually go to 0 because L is only getting bigger and we're always doing subtraction on it. So I'm surprised it didn't hit the break. What I could do is print a few things. I could print L is equal to L and num rhombi is equal to num rhombi. I'll just also make sure that my n and L should be right. I don't know why that would go wrong. Print m equals m, n equals n. What am I doing? N equals n. There we go. I mean, a while true. Ooh, okay. A while true loop was always going to be a bit risky. Okay, so that's bad. Ooh, wait. Huh? M is equal to 5, n is equal to 5. When this one is equal to 2, you have m minus 4 times, so you have 5 minus 4, 5 minus 4. Ah, because you're getting two negatives. Two negatives make a positive. Ah, of course. Okay, so maybe I'll say the minimum of this and 0. So if it goes negative, it bumps up to 0, and the minimum between this and 0. The formula looks a bit more confusing now, but it should now terminate. What? Oh, sorry. Damn it. You serious? That's not good. Okay. Print R equals R and C equals C. Also print the L. I'll already print the L value. Wait. What? What is the final case? Grid is 3 columns, 1 row. It broke straight away? Does that make sense? Oh, because no, but for L equals 0, it shouldn't have broken yet. It should have been M minus 0 times N minus 0. Should have been M by, yeah, I should always get the M by N case, surely. Alright, let me do this up here then. Oh, damn, I gave myself half an hour and I've... What? Max. Sorry. Of course it's gonna always go to 0. I was thinking min, like, I don't want the minimum. I don't know what I was thinking. Anyway, it's fine. Okay, that's pretty good. Do I back it? I feel like I do. I don't know where else it could go wrong. I mean, again, I put min instead of max, so that's fun. But, I mean, and this bit is really crazy. Like, this is really stupid, but I could clean it up, I guess. Hang on, let me think. So how would I want to do this? I could do, like, a priority queue. That feels like a bit much. considering I'm only storing 3 answers. I think a list is fine, and I think doing this is also fine, because like I don't really think it's a big deal. And then yeah, I mean, look, it's fine. It's a bit ugly, but computationally it's fine. I am a bit worried that I've missed something, but I don't know. Oh, shall we? Let me print what the 3 biggest sums looks like. Make sure that that's where it failed. I don't know. I mean, this still normally happens, but of course, it's such a massive test case. So there must be some logical issue. Yeah, so they got all the same number, which is annoying. Is it because? Hang on. Is it because they said the 3 distinct? How do they say it? Hang on. Yeah, okay. So I understand. Basically, there are 3 rhombi with the same size, but you're not meant to count them. So honestly, a priority queue might be. No, that doesn't work. It won't hold the set. So what? A set then? I thought, yeah, I didn't read the question very well then. That's my bad. Set, oofed. Yeah, I mean, I think, to be fair, I mean, look, the computationally expensive part is doing all this traversal. So if 3 biggest sums, just do this, dot add the R sum, do this. This will give me all the R sums basically. Then, yeah. No, wait, hang on. I see. Yeah. Okay. Sorry. For a second, I was like, wait, why did it return? Like, why is this case 7? Like, why they only gave return 1 answer? Then I realized literally all the rhombi are 7. Like, you can't avoid it. But if you can avoid it, if you have a tie. But what happens if, like, you only have 2 rhombi sums? If there are less than 3 distinct values, return all of them. Right. Okay, I got you. Yeah, okay. 3 biggest sums. We'll make it a list. And we'll say answer equals that, and then answer dot sort reverse equals true. And then if the length of answer is less than 3, then return just answer. Otherwise, I think you're safe to return answer from 0 up to 3, because I will get 0, 1, and 2. And I spelled return wrong, which is fun. Yeah, that's a misread of the question there. Or I forgot it at least. Yeah. 47 milliseconds is a bit unfortunate, but hey, I did the computational check. Like, I made sure that. Did I print anything? 1, 2, 3. Okay. And submit. There you go. Okay, so it's, yeah, you can see there's 2 peaks because this is like brute force section, and then this is probably something cleverer. Is there anything okay, so now that I've gotten the solution done, is there anything I could have done better? Like, I'm trying to think like a way of remembering kind of, like, for example, right? Hang on. If I consider like the biggest rhombus, which is this one. If I'm trying to save on efficiency of like how to solve, like how to find the sum quickly, is it somehow beneficial maybe to remember that, you know, this guy here has a particular sum, and like, because like you see this, like one 2x2 is made up by four 1x1s, right? So I'm trying to figure out, like, if you do it like that, if you were to add this guy plus this guy plus this guy plus this guy, and then just subtract two lots of this guy, 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 then I believe you would get the sum of the red. You know, like you make sure to balance it out by getting rid of the excessive blue edges twice, because you're going to add them twice when you do this. But then, you know, then you have to keep track of like these guys, and I don't know if that's more weird. But maybe it works. Maybe it works. I'm not sure. Anyway, let's read the better solutions. Something over here. Some of these might be ridiculous, but some of these might be really cool. Prefix sum of the diagonal. Oh, wow. Rows and columns, length of grid, length of... Fine. Left diag is x for x in y in grid. So for each row in grid, for each x in... Wait, what? So for each row in the grid, for each x in y, isn't this just for each value in the row? And isn't this just going to give you all of the... This is the same thing. So I'm assuming they just duplicate. This is just a copy operation, right? Unless I'm really misreading that. But yeah, so you copy the grid twice. And then for I in range rows, for j in range cols, if I plus 1 is less than rows, that is to say that I plus 1 is a valid index, and j minus 1 is greater than or equal to 0, which is to say that j minus 1 is also a valid index, then left at one row down and one column to the left is added on from the current. So you're basically doing like a cumulative, yeah, so prefix sum of the diagonals, fine. And then same thing, if I plus 1 is a valid index and j plus 1 is also a valid index, then the value to the down and to the right, you add on from the previous value. So you're cumulative summing from top left to bottom right and top right to bottom left, I think, yeah. Because you're going, yeah, this is going to the left. Okay. Is that right? No. Yes, it is. Wait, but you're going up in J. Am I tripping out? J minus 1, I plus 1. So you're going down a row and to the left. Plus equals left diagonal of I and J. Left diagonal. Going from ij to I plus 1 j minus 1. The left diagonal. And the right diagonal is like going down and across. This makes sense to me. This time I don't know why. It feels like it should make sense to me, but the fact is j is getting bigger. So I guess it does make sense though, I think. It does kind of work. It's just that you would be, the way the cumulative sum would be read, I think, from bottom left to top right, I think. Anyway. Traverse the matrix to find the matrix rhombus sums. Sums equals 0 for I in range rows, for j in range columns. Max length is equal to rows minus I plus 1. This is interesting. Oh, heap Q has an n largest. That's pretty cool. Anyway, sorry. For I in range rows, this max length, I'm assuming is just getting that L value, the biggest L value you can get, which I guess this formula lets you do, which is pretty cool. Print I, J, K less than equal to, okay, that's right, that's not important. Max length. For K in range max length, so I'm assuming K is like my L, like it's the side length. If it's equal to 0, if then just append this. Otherwise, sum 1 is equal to left diag. Ah, it's doing all the diagonals. Yeah, that's clever. Because it lets you basically really quickly find the sum between these 2 points. And I think the sum between these 2 points, and the sum between these 2 points, and the sum between these 2 points. That's better. Yeah. Sum 1, sum 2, sum 3, sum 4 is a constant time operation. So for any rhombus, you do find you have a constant time thing. See, so mine was my summing, because I kept traversing over the entire sides. That's clever pre-processing. I imagine the time complexity is better because you're not doing that extra traversal. So you just stick with like an m by n thing, I would assume, is my understanding. But yeah, pre-processing on the diagonals is smart. That's pretty cool. Nice. Okay, fair enough. All right. Oh no.